We just saw how we store and access basic arrays in memory by putting all of their elements, one right after the other, in a contiguous block of memory. In this video, we're going to take a look at multidimensional arrays or nested arrays where we have more than one dimension. So let's take a look at a quick example here. Let's continue with our zip code motif. Here we have an array that's two-dimensional. It's nesting the zip codes of multiple locations in a single array. So here we see 4 different zip codes contained in an array, each one of which has 5 elements, the 5 digits of the zip code. So remember that in our declarations, when we write an array of some type with its name and number of elements, here we see that the number of elements is this value p count, which is defined in our C code as being 4. The name of the array is SEA, probably meaning zip codes in Seattle, and the type is zip digit, that type we've seen before for representing the 5 digits of a zip code. So here we have our 4 zip codes, each represented on a separate line. You'll notice there's closing brackets around all 4 that define the entire array. The way this is stored in memory is also contiguously, but we have to decide, of course, how to store the multiple zip codes now. So you'll see we have one zip code here, again arbitrarily starting at an address 76, but that could be anything. It depends on how memory is allocated in our system. Here we see the 5 zip codes of that first value, 98195, and then it's immediately followed by the next one and the next one and the next one. And these are in what is called row major order. In other words, we've taken one row of the array and completely put that into memory one right after the other as if it was a one-dimensional array, and then follow that by the next row and all its 5 elements, and then the next row and its 5 elements, and so on. This is a guaranteed organization in memory. We can rely on this. So when we write something like this access to the SEA 32, that means we want the 4th row, the index 3 starting at 0, so it's the 4th row, and then the 3rd digit within that row or within that zip code or that zip dig type, and that's the number 1 represented in that location. Okay. All right. So in general, when we talk about multi-dimensional arrays, and in this case we're still looking just at purely 2-dimensional, we have a number of rows and a number of columns, and in our declaration we can just put 2 brackets right after the other, one with the number of rows, one with the number of columns. That's going to generate that 2-dimensional array as we've seen in the previous example with R rows and C columns. Each element of that array is going to require k bytes to represent whatever the size of that element is. In the case of the digits, it was a simple integer. It was just 4 bytes, but that could really be any data structure. Okay. So our array then in general is of size R times C times K, where R and C are the rows and columns, and K is the size of an element. And again, arranged in row major order. So we see the very first element here at 0, 0, the 2 indices, and then that'll be followed by 0, 1, 0, 2, all the way to 0, C minus 1 in this location. Okay, then we start the next row with starting index of 1, 0, all the way to 1, C minus 1, and then we'll put the next row after that. Eventually, we'll have the last row represented by those indices. Okay? And if we're talking about integers, as in this case here, we've declared an integer array, then this size of this entire area of memory will be 4 times the number of rows times the number of columns. Okay, so how do we access the elements of this array? Well, again, let's start with the starting address of the array. The starting address of the array is represented by the name of the array, A in this case, and the very next row of the array is going to be how far down in memory. Well, it's got to represent all of the columns in that row and then the size of the data element. So every row is of this size, number of columns times the size of the element, and then of course the index is used as a multiplier on that. In this case, again, for integers, k is 4, and we're multiplying by the index. So the row starting at index 1, which is the second row, would be at a plus c times 4. Okay. The very last row would be at a plus r minus 1 times c times 4. And we could easily have the starting address of each row by doing that basic arithmetic. Okay, so let's take a look at an example here. Here's our array again that we saw earlier, a 4 by 5 array of 4 zip codes of 5 digits each. And we have here a little procedure that returns a pointer to an integer, okay, and is given an index as an argument. And what it does is it returns the starting address, the pointer to the starting address of the zip code at that index. Okay, so if we ask for the 0th zip code, we would return the starting address. If we ask for the first zip code or the second element at index 1, we would return the starting address of the second row, and so on. Okay, the code for implementing that basic little pointer returning procedure is to compute an address. So we use that effective address computation instruction. And you'll see here that what we're doing is taking the index that was in EAX and multiplying it by 5. Okay? And we can do that using that LEAL instruction. Then we take that index, that value, 5 times the index, and multiply it by another 4. Remember, because we can only put powers of 2 in that instruction, we can't just multiply by 20 right off the bat. So we have to do it in 2 steps. We get 20 times the index. And why do we go after 20 times the index? Well, because we're going to have 5 elements in each row, and the elements are of size 4. They're just integers, so that means each row is of size 20. Okay? And we're going to do 20 times the index and add that to the starting address of the array, and I've just shown it here as the offset for the LEAL instruction. Okay. So that's the starting address that's computed and returned by this procedure. All right, we have to do it in 2 steps again because of the constraints on the LEAL instruction. All right, let's go another step further and look at how would we compute the address of a particular element, let's say element aij for the most general case. Okay, so how would we compute that? Well, to compute that address, we would first have to get to the beginning of the row, right? And then do an offset within the row to get to the address of that array. So you'll see that our address is the starting address of the array. Actually, that gets us here to begin with. And then we have to offset by the number of rows that we're going in. So our first index, the number of rows, times the column times the size. Remember, C times K is how much space a row takes up. And then we just multiply that by the number of rows we need to offset. We're now at this point. And then we need the offset within the row. And for that, we need the second index J, the number of the column, times the size of the element. And that will get us in as far as we need to go to get to the ij element. Okay, so in general, we can simplify that to that expression, I times C plus J times K, and then offset that from the starting address of the array. All right, let's go back to our example, but now we have a different procedure. Same array, but a different procedure that computes this time just an integer that is the particular digit of one of the zip codes. So this takes two arguments, the index as well as the digit that we want, the third digit or the fourth digit, so on. It returns an int, of course, because now we're not going to be returning an address, we're going to be returning the actual value of that digit of the zip code. Okay, so let's take a look at the C code for this. That's pretty simple. We first index into the row of the array and then to the right column or to the right digit position. Okay, the way this is represented in assembly language is using a couple of LEAL instructions and then a move instruction to actually get that digit value out of memory. And let's see how we do that. Assuming that we've put the digit in ECX at the beginning, what we'll do is use an LEAL instruction to just compute 4 times that index. That would be that J times 4, okay, to get us the offset within the row. Then we need the offset to the right row. And remember, what is that? That is just that 20 times the first index again. So here we do that times 5. And then we're going to have to multiply that by 4. And we'll do that as we do the actual memory access. So you see here, we'll take that 5 times the first index, 5 times I value, and multiply it by 4 to get 20 times I, or 20 times the index. Add to that the 4 times digit that we stored in EDX. And that gives us the complete offset into the array, and then we just need the starting address of the array to add that to get us to the right memory location. We get the value at that memory location and store it in EAX, ready for returning from our procedure. All right, so that's the general process, and you'll see these kinds of expressions often, these little groups of instructions that compute an address and then go and actually access the memory. Let's close this up with some addressing examples, different accesses to our array. Here we have our array shown again as it's represented in memory, contiguous part of memory. And let's look at our first access, 3, 3, looking at that location. What address should that be? Well, remember we have to multiply that first index by 20. So that would be 3 times 20 or 60. And then the second index is multiplied by 4, the offset within the row. So that's another 12. So it would be 72 total plus the starting address of the array at 76, which puts us at 148. And the value of that element is this one right here, the 1. Remember, it's the 4th row, the 4th element, because of our indices are off by 1. They start at 0. So we see that the address is 148, the value is 1, and this is in fact guaranteed because of our row major order for how we store these arrays. Our next example is C25, and you'll notice that that 5 seems to be out of bounds. It's too high an index for our array. We would only expect to go up as high as 4 for the 5th element. So this is probably not a correct construct, but in C, the same address computation is done. So it doesn't check for those bounds. So what would happen in this case is we would compute an address based on that first index times 20 and the second index times 4. Adding all that up, we get 136 as our address, and the value is 9. And the 136, you'll notice, is this location, right, which is clearly not the third element that we seem to be looking for here, the third row. It's one beyond that. But because of how we arrange things in memory and row major order, we will in fact always get a 9, and this value is guaranteed to be consistent, even though we're using the wrong index. Similarly with the next one, with a -1 for an index, which is clearly out of bounds, but the same address computation is done, this time yielding 112, or 1 before our row of interest. and the value there is 5. And again, that's guaranteed because of the row major organization. When we do 4 minus 1, that's again a little bit out of bounds. We've gone beyond the memory, but because of the minus 1, we yield an address of 152, which is this location here, and the number 5 is guaranteed to be there. Okay. Finally, 019 address computation is that same exact location done in a very funny way. We've sort of gone over the bounds of our first row and just kept going and ended up in the same location. While the previous one, 4 minus 1, we actually started 1 outside the array and came back in and looked at that last element. But those are in fact addressing the same location. The last example here, of course, 0 minus 1 puts us at this location, and minus 1 from that, and that would be the location here for which we have no idea what is in that location. And there's no guarantee as to what we'll find there because it depends on how things are arranged in memory. So the important thing from this is that, remember, row major order for the order in which things are arranged in multidimensional arrays. And we can actually use that to our advantage sometimes, but it's probably best to stick with array bounds that are within range.